Hello, everyone. This is a lecture on carbohydrates. So we're starting the biochemistry portion of the semester, and we will cover carbohydrates, lipids, and amino acids. Before we begin, be aware that this is only a kind of like a survey, an intro with some organic chemistry in the organic chemical context, meaning there are some reactions that you have to do. We'll do the basics enough for you to understand about carbohydrates. But the one thing that I wanted to say was that an understanding of organic chemistry is necessary to understand biochemistry. You will see that plenty of these concepts in biochem are based on organic chemical concepts like bond breaking and bond making. So let's pay attention and learn this interesting material. Now, I don't have to probably tell you how important this lecture is or this biochemistry is. Everything in the medical field is based on biochemistry. So let's begin with carbohydrates. Carbohydrates are also known as sugars and starches. Carbohydrates are an abundant molecule. More than 50% of the carbon in organic compounds is found in carbohydrates. So it's dense, very dense material. And plants use photosynthesis to store energy in glucose, a simple sugar. Of course, in your body, we know the abundance of carbohydrates as a source of fuel, but of course, other things in biochemical processes. So it's vast. We don't know where to begin because of how vast it is, but let's learn the chemistry of it. So for example, this is a quick reaction of glucose synthesis and metabolism. You know that plants take in carbon dioxide and water with light using chlorophyll to convert that into glucose and oxygen. And you notice that energy is stored this way, going from left to right, but really it's the other way. So that's metabolism, that's photosynthesis or cellular respiration, the metabolism one. So carbohydrates are a large class of naturally occurring polyhydroxy aldehydes and ketones. So you see the organic chemistry in this, aldehydes and ketones. Monosaccharides are also known as simple sugars, are the simplest sugar carbohydrates containing 3 to 7 carbon atoms. A sugar containing an aldehyde is also known as an aldose. An aldose. A ketone is known as a ketose. So an aldose and a ketose. The classification of carbohydrates. Carbohydrates are grouped into 3 classes. So we just talked about one of them. That's the monosaccharides. So monosaccharides are the simplest sugars and serve as the building blocks of larger molecules. For example, glucose is a monosaccharide. You have one that's called oligosaccharide or oligosaccharides. Those contain 2 to 10. Again, there are some, I guess, slight disagreement. Some people still consider more than 3 to maybe 7, like I said, are monosaccharides, but I'm going to use the traditional, which say, oligosaccharides can contain 2 to 10. And then, of course, lastly is you have polysaccharides. those contain a lot. Those are much more complicated structures, and they're in starches, etc. Very well. So that brings us to the monosaccharides, because again, the bulk of this discussion is going to involve first monosaccharides, and then we will move to polysaccharides, etc. So monosaccharides, as we said, they're polyhydroxy ketones or aldehydes with 3 to 7 carbons. Very well. So poly means more than one hydroxy. So you have multiple, you can say you have multiple OH groups in the compound. For example, look here, this is glucose and aldohexose. Notice how it has multiple, it's polyhydroxy. You have plenty of hydroxy groups attached, and it's still an aldehyde. You see the C double bond OH, that's your aldehyde right here. Okay. You also have ribose, which is a component of ATP, coenzymes are RNA. It's an aldopentose. Okay. The reason why, by the way, it's called an aldopentose. Pentose comes from pentane, which means 5, because you have 5 carbons, 1, 2, 3, 4, 5. And of course, it's an aldose because it's an aldehyde. Whereas you have a ketose here, which is fructose. Fructose is a ketohexose. It's present in corn syrup and in fruit. So here is your monosaccharides. These are 3 examples of monosaccharides. So how do we name them? We name them monosaccharides with an aldehyde carbonyl at C1. Those are called aldoses, as we said. And then if we have monosaccharides with a ketone carbonyl at C2, those are called ketoses. So look here. So we're going to number these. You've got 1, that's 2, 3, 4, and 5. So you say it's an aldopentose. 5, remember, it's penta. So that's, and you have an aldehyde here. So that's why it's called an aldopentose. Whereas here, right here, obviously you start the counting from here, longest chain, but pay attention to this too. That's where your ketone is. And you have 4 of them. So you call this a ketotetrose. Tetra means 4. So once again, keto, tetrose, aldopentose, aldohexose, whatever it is. That's the idea. So if you have a triose, that's 3 carbon. If you have a tetrose, that's 4. If you have pentose, it's 5. And a hexose, you have 6, and so forth. So if we were to, let's say, have a compound here, and draw that compound as an understanding check. So if we have this, one, 2, 3, let's say 4, 5, 6, and 7. Okay. So if you have this, So I know it's not, the drawing is not the greatest, but you can see here. So we start counting. We say, okay, here's 1, 2, 3, 4, 5, 6, and 7. What do you have, an aldehyde or a ketone? It's an aldehyde. So you call it aldo. And how many do you have? 7. So what's 7 from heptane? Yeah, it would be heptose. Aldoheptose. That's all. Very well. So let's go on to the simplest aldehyde is called glyceraldehyde. And the simplest ketone is dihydroxyacetone. And you're going to see them next year. So that's critical because it brings us to stereoisomers in carbohydrates. So stereochemistry is apparent everywhere. Carbohydrates are chiral molecules since they have carbon atoms carrying 4 different groups. Very easy to tell. So if you look at D-glyceraldehyde, which is the simplest aldose, look here. So you have 3. That's the simplest. You can't have anything less than that. That's chiral. Why is it chiral? Chiral means it has 4 different groups. Well, here's my chiral carbon. I have an OH, that's 1. I have an H, that's another group. 3rd group, and the 4th group. 4 different groups. Okay. And it has an enantiomer, which is L-glyceraldehyde. And you can see here that they are stereoisomers. They're enantiomers. So remember, compounds with N chiral carbon carries or has a maximum of 2 to the N possible stereoisomers and half of that many pairs of enantiomers, mirror images. So if we, for example, if we have an aldotetrose, that's 4, you have 2 chiral carbons here. I'm going to put an asterisk right there, a star, 2 of them. So we say, okay, 2, how many chiral carbons? N is, you have 2 chiral carbons. Or stereocenters. So 2 to the 2 is 4. And you do have 4 possible ones right here. Of course, it gets to other things like mesoisomers. So be able to, again, apply what we learned so far. The D and L families of sugar, very, very important. And you always hear about that. So please pay attention to this. A D sugar has an OH group on the stereogenic center, farthest from the carbonyl carbon, okay? The farthest, it's the farthest from the carbonyl carbon. Look how you have an aldehyde here. That's basically this, your aldehyde. All the way down, okay? And if you notice here, the OH is on the right side. If it is on the right side, you call that D sugar. It's a D sugar. Whereas if it is on the left side, okay, if it's on the left side, then that would be an L sugar. And that comes, in a sense, comes from levorotatory and dextrorotatory, if you remember that from Organic 1. So once again, notice how this is on the left. And we call it L. Okay, one way of remembering is, again, just remembering 1. If OH is on the left, then that would be an L sugar. Obviously, if it's not on the left, then it must be what? A D sugar. So be aware of that. So let's look at over here. Now, you have the family of aldoses. So if you look here, we start with the simplest. So we start with, those are aldehydes, remember. Glyceraldehyde, then you go to, if you have 4 over here, those are the possible ones, by the way. You have D erythrose and D threose. And then if you increase it to 5, that becomes now, of course, multiple ones. If you see the flow chart right here, notice how one thing I want you to pay attention is that you're adding, okay, another chiral carbon. Like, for example, here, we added in this OH and the H in addition to that one. So here it is. That's the new one. I'm circling the new one. Okay. But we flipped that one, okay? Or you can think that we added it to the top, so on and so forth. It doesn't matter in this case. But now, notice how you have now, with 5 sugars, notice that the difference between them, basically these are stereoisomers of each other, are actually they have names. So we don't just call them diastereomers of each other, like D-ribose and D-arabinose. Those are diastereomers of each other. Okay, so those are diastereomers. Now, these. Same with these here. Now you have D-ribose. You should know that one. You should know it really how it looks like, where you have all the OHs, that it's actually a pentose and aldopentose, that it has all the OHs, all the hydroxy group on the right side. You have xylose, arabinose. All of those are really critical when you get to the biochem. But most important ones are down here with the 6, where you have D-glucose, D-allose, D-mannose, glucose, etc., galactose, etc. All of these, once again, notice how with 6 carbons, you're adding again another chiral carbon. And like, for example, let's look at from D lysose. That's a Z, pronounced as a Z, the X. If you notice here, you have the OHs on each side, on the right side here, on the left side, and then that one on the right side. And notice how the D-galactose is a little bit different. You just basically added one more. Here it is on the top. This one, you actually added another one also on the top. But again, they are on different orientations here. Okay, so of course, glucose is very important. I would, if I were you, remember this, how that it's 6, and it has the OHs, all of them on the right side except the second one, on the right except the second one, which is on the left side. You have mannose. All of these are important. Make sure you remember what this means. Diastereomers that differ in configuration are around only one stereogenetic centers are called epimers. So for example, look at mannose and glucose. Okay, look at mannose and glucose. Mannose and glucose are similar in 3 stereogenetic centers are similar. Okay, stereogenic centers, okay, similar. Here they are. The only one that's different is the one on the top. So those are called epimers. Epimers. However, glucose and maltose are not epimers because they're different on multiple ones. So there would be diastereomers. So again, they have to be different on one, just one stereogenic center. Okay, we have the family of D-ketoses. So we talked about the aldoses. Now we're talking about the ketoses. Remember the ketones. So you have dihydroxyacetone. It's basically like acetone. This is acetone right here. but dihydroxy looks like this. Has the CH2OH. Then what happens is if you add one carbon between C2 and C3, like it's kind of similar to, well, maybe not. If we had one carbon between C2 and C3, so between C2 and C3 right here, again, you have now 4, and that has a name. Then if you have 5, notice again, you're adding in between. And then you get to, of course, like one of the most important ones, which is D-fructose. Notice that you have, again, a OH on the left side, the first one, and then the other one's on the right. Okay, what are the physical properties? So make sure you remember the structure of D-fructose. What are the physical properties of monosaccharides? They are all sweet tasting sugars, and their relative sweetness varies a great deal. Yeah, big deal. They are polar compounds with high melting points, and the reason why is because they have lots of hydrogen bonding. Here it is, hydrogen bonding. And hydrogen OHs are polar bonds. Okay. And the presence of many make them water soluble. That's why they're water soluble. And unlike most other organic compounds, monosaccharides are polar because they are insoluble in organic solvents like diethyl ether. So they're actually very, that's rare. So they're insoluble because they're so polar. They're highly polar. So they can't dissolve in polar solvents. So they have to dissolve in water. So you can add sugar to gasoline, and we know what that does to the, it's not going to dissolve. And you, again, people add that to cause damage. But anyway, so let's get back to an important form. So monosaccharides, they have their cyclic forms. So we need to pay attention to this. So we didn't learn anything in vain here. We learn everything, for a reason. For example, we said when we have an alcohol, an aldehyde, and we add an alcohol to it, we get something called a hemiacetal. You can go back and review your notes, right, in the previous chapters on hemiacetal. And I said to you, we're going to revisit this. We're going to revisit it when we get to carbohydrates. So you actually, what happens in the cyclic form is you form a hemiacetal. A hemiacetal is basically, you have an OR group, an ether, you can say, and you have an OH group. So you have an alkoxy group and a hydroxy group. So we need to learn how to do this. A monosaccharide contains both an alcohol and an aldehyde group. And it can react with itself to form the cyclic hemiacetal. Very well. So look at D-glucose. D-glucose can react with itself the following way. And you have to keep this in mind all the time. It's going to become a cyclic structure via the reaction of this oxygen right here and that carbonyl. So again, it's the hydroxy, not on the 6. The common mistake is they think it's on the 6. Well, it's not. It's on the one on the 5th. And here's where the hemiacetal forms. So you might say, okay, where the heck is the hemiacetal? I don't see it. Yes, here it is. Here's the OH, and here's the OR. Okay, or whatever, the whole thing. So OH and OR. So again, you have to look at it visually. Aside from this, because it's not really helpful to just attach it like this, we're going to have to actually learn how to do it and how to draw it. And you're going to learn it right now. Here's what you do. what you do is the following, is when you're giving the glucose, or if someone, let's say, or not, or anyone that maybe anything that, let's say, like galactose, whatever it is, you draw it, and then you want to turn it this way. This is really helpful to turn it this way. What you're going to do is you're going to start drawing the skeleton for a 6-membered ring to the sides, kind of like this. This is what you want to do. You want to start by drawing this. So I'm going to draw it one more time so you can see it. So the first thing you want to do is, again, you want to draw this. Okay, don't close it yet. When you do that, you want to attach everything that's on the structure. So we start with 1. Your 1 starts here. You start counting from this one. So you go, this is your 1, that's your 2, that's your 3, that's 4, and that's 5, and that's your 6. Okay? Now, what you do then is the following, is you start attaching all the necessary compounds. So you say, okay, I have a C, double bond, O, with an H. Then I go to 2, and this is very, very critical. This is very, very critical. The direction here is important. You can't just put the OH anywhere you want. Okay, now think about it. If we move this 90 degrees, we moved this way. We moved it 90 degrees. Okay. You know the OH, this OH is going to be down, not up. So we put that down. Okay. Then if we move this down, then this OH will be up. This OH on 4 is down. And then the one on 5 is also down. Okay, we're going to do, and then more on the next one. And then, of course, what's attached is you have this CH2OH right here. Okay, let me erase this so you can see. Okay, let me erase the numbers so you can see them. Okay, now before you move on, you say, okay, I'm ready to react them. You might be inclined to say, okay, here it is. I have a lone pair. I have 2 lone pairs on this. I'm just going to attack. No. It's not between this OH and the carbonyl and the aldehyde. It's between this OH, this one right here, and this carbonyl. So be very careful. What you want to do then is you just want to switch them, just like this picture says here. So you move this up, and you switch them just like here, down here. And then what you do is you form a bond, and you remove that H. Of course, this bond has to break. Well, it gets protonated, and you're not done. You still have to do one more thing. You have to say, okay, well, is the OH now after this gets protonated, it gets like a minus, and then, you protonate. So the question is it going to be up or down? Well, it's both, up and down. And we call this the anomeric hemiacetal. And if it is up, this is called a beta. And if it's down, the OH is down, that's called an alpha. It's enormously important. Okay, so this is called the Haworth projection. It's used a lot in the biochem, but we're also going to learn how to do the chair structures. So cyclic forms of monosaccharides are drawn the Haworth, as we said. The edge of the ring is closest to the viewer, so meaning that this is closest to you. Substituents on the ring in the Haworth projection are either up or down, like we said, are either down in this case or up. So for these sugars, the alpha anomer has the OH pointing, what did we say, up or down for alpha? It's down. And for these sugars, the beta is pointing up. And here they are. Okay, we're going to have to learn how to also do the chair cycle. Remember the cyclohexane chair structure, because they're both valid. So here's how you transform them. Draw the chair like this. So notice the relationship here. Your O at least is still in the same position. Okay, it went down, up, down, up, up, down. Okay, and then all you have to do is, you really have to pay attention to this, is ask yourself, okay, where are things pointing? So this is a very important picture here. So the OH, in this case, it's a beta. This is beta because it's pointing up. That's the anomeric carbon. So it's pointing up here, or equatorial. Well, next, the OH is pointing down, so you have to make it point down. The next OH is pointing up, so you have to make it point up. So what's critical for this is make sure you review your axial and equatorial positions. Go back to organic 1, or at least they're shown here. These are equatorial, so I'm going to show you, I'm going to circle all the equatorial. So this is the equatorial position. This is equatorial. This is equatorial, equatorial, and of course, equatorial. The axial is the up and down. They have to be 180 degrees, up, down, up, down. These can be to the sides. But of course, we're looking at it from a different perspective. So here's the alpha anomer. OH is down or axial. And here the OH is equatorial. So keep that in mind. Very well. Let's actually draw the structure of both for D-galactose. Let's start with the Haworth projection. So you're going to need some space for this. So I may run out of space. So I'm going to probably need more than this, or probably end up erasing. So if you need more space, go ahead and find another sheet of paper and add it, because I'm definitely going to erase. So this is what I'm going to do. I'm going to flip this, okay, move it 90 degrees, just have it, make it flat. And watch how I'm going to do it. So I start with the carbonyl here. Here it is, it's flat. Okay. This is pointing down now as I moved it 90 degrees. This is now pointing up. This is now pointing down. And the OH, I'm sorry, the OH is pointing up and the H is down. I'm going to number them for you. This is down. And then, of course, I have the, no, this should not be here, but OH. Okay, so let me number them for you. Here's 1, 2, 3, 4, 5, and this is 6. 1, 2, 3, 4, 5, and 6. So take a moment to see how each is, as I moved it 90 degrees. Okay, move it this way, 90 degrees. Tilt it and see how it looks like. Okay. So again, the OH is 2 is down. Those are both up, and that's down, etc. All right, so let's begin now with the Haworth projection. So what I do is I draw the skeleton like this, and I start. This is my C. And by the way, I'm just showing you the mechanism also through this. Okay, now let's move to 2. It's down. 3, it's up. 4, it's up. And then 5, it's down. And of course, I have this, CH2OH. Now, I have to switch these places. I have to switch them, those. So the OH is going to go there, and that's going to move up. So it's going to go like that, as we shown in the last or few slides ago. So okay. So when you do that, you get the following. And again, we switched these. So this one went up. That one now went there. Okay. Now I need to show what happens. And of course, the protonation takes place. So now let's just draw the final product from this. Like I said, I'm going to need to erase so you can see. Okay. So now it's going to look like this. Okay. Now I either have alpha or beta, so I'm going to draw both. I'm going to start with the beta. Okay. Let me just, it's not at a good angle, but it's good here. My second OH. Okay, here it is. That's my beta anomer because it's pointing up. My alpha and I hope you can see it, my alpha will be the same except the anomeric and here's my alpha. Very well. The cyclohexane. So do enough of these. You can go back and practice. Make sure you do. You can go back and pick any of these and work on them. I also have questions in the worksheet, so be sure to check it out. All right, so let's look at the cyclohexane structure. Very well. So here's your frame of reference, the O. All right, start with this O, H here. So I'm going to number them on the top so you can see it. Say this is 1, that's 2, 3, 4, and 5. 1, 2, 3, 4, and 5. Of course, that's 6. It's going to be pointing up. So on 1, I see it that it's pointing down, so that must be axial. Otherwise, if it's equatorial, it's pointing up. On 2, it's also pointing down, so it must be equatorial. Otherwise, if I move it axial, it's going to be up. OH is up, so it's equatorial. So again, that's 1, 2, 3, 4, pointing up, so it's axial. And of course, we have the CH2OH. Simply, it's always like this. Now, for equatorial, for beta, it's the same thing, except this is now equatorial. So it looks like this. And everything else stays the same. So that's a good thing. All you have to do is master how to do the alpha and the beta. So this is beta and this is alpha. Be sure you're able to do this. Okay, the cyclic forms of monosaccharides can be named as derivatives of the heterocyclic ether furan, 5 members, that's what furan means, and pyran, which is 6 members. So if you can have a furanose ring where you have 5 rings, 5 carbons, and by the way, it's the same process, nothing new. You just, it has now a ring that looks like this. And you can have, of course, so you can have a furanose ring or a pyranose ring, which means 6. So you say that you call this beta D ribofuranose ring, because again, it comes from ribo, it's 5. This is ribose. And the furanose is a 6 ring. Okay. Reactions of carbohydrates. There's not much we can, I mean, you have to know, okay, know all reactions, know all, be able to draw products, etc. There's not much we can do. That's all I need you to tell, I need you to know is be able to draw the products. And here you go. So if you have a reaction of a hemiacetal, and this is nothing new, by the way, only the hemiacetal OH reacts. So meaning that if you have this reagent, alcohol, acidic environment, you're only going to make a react only this, only the hemiacetal OH, only this. Notice these are untouched, all of these. These still remain the same. So look, see, nothing happened to these on either side. Nothing happened to them. This changed. And once again, you have an alpha glycoside or a beta glycoside. Well, what about the hydroxy group? Can you do that? Yes, you can. But now you have to use a different reaction. So these are two different reactions. They have two different purposes. If you only want the hemiacetal OH or the anomeric one, then you do the alcohol and acid. If you need the silver, if you use the silver oxide and methyl iodide, then you would have to actually make or methylate, I would say, we say methylate all of the OH groups, all the O's here. And notice that this one is there. And next is you have reduction of alcohols. Reduction, remember, means less C double bond O in this case, or C. Let's look at the classical. Less CO, CN, CX bonds, of course, mostly, here, and you have more CH bonds. And here it is. You basically went from this on this side, the aldehyde, to this on the other side. So here's your reduction. So this is now sorbitol, glucose. Oxidation is the opposite. You actually, and again, make sure you remember this is nothing new, by the way. We use sodium borohydride, reducing agent. Nothing new, nothing new. Those are old reactions from the aldehyde chapter. And reduction or oxidation is your increasing. So you go more for oxidation. You have more CO, CN, CX bonds, and less CH bonds. And we can see this is happening. You have less CH bonds on the other side. You have now more CO bonds. You have an additional one. And again, these are the over here, these are the reagents. Also, we used this before, Tollin's reagents, if you recall that. And Benedict's and Feeling's reagents. And they give you actually a positive test. So if you go from blue to red, then that's actually a positive test, meaning, it took place, the reaction did take place. Okay, then you have reducing and non-reducing sugars. This is very, very important. Hemiacetal, right here, it's a reducing sugar. But over here, when you get to an acetal, and why is it an acetal? Because we have two OR groups. Here's the OR group, and here's the OR group. That's why it's called an acetal. OR, OR. Hemiacetal is OH, OR. So you have reducing sugars. Those are reducing sugars. So it says carbohydrates containing a hemiacetal are in equilibrium with a cyclic aldehyde. Basically, the structure we've shown, they're always in that structure in between the ring and the long chain. I'm talking about this. Let me go back and show you. I'm talking about this right here. Yeah, these are in equilibrium with each other. This one and that one. So making them reducing sugars. Glycosides are acetals, so they are not in equilibrium with any acyclic, making them non-reducing sugars. Okay, so those are called glycosides. And we're going to learn about why they're called that and actually be able to put the structures together. So Very well. So reducing and non-reducing. There are two more reactions, so make sure you remember these. The wool degradation shortens the chain by 1 carbon, so you can go from 6 or 5 to 4. The Kilani-Fischer, it's the other way around. It increases or adds 1 carbon to the chain, as an example. So here's the wool degradation. If you look here, you see that if you have this glucose, D-glucose, notice what happens on the other side. You eliminated this carbonyl, or this chiral, one of those chiral carbons. So again, it shortens the chain by 1 carbon. So this was removed, as you can see. So you went from D-glucose to D-arabinose. These are the steps. All I ask from you is, again, just to know what wool degradation does. So you don't actually have to know the reagents per se. There are too many. Just be able to know, if I tell you this is wool degradation, what does it do? And be able to remove the top one. And the Kilani-Fischer does the opposite. It increases. And notice what happens here. These are still the same on each side, but it added 1. Now, once it adds 1, it has to make a set of, or pair of epimers. Because again, who said you're going to need to add only OH to the right side? It's both. So you get a 50-50 chance. OH on the right side or on the left side. And that's why you get epimers. And these are the steps. Once again, I don't need you to know the steps, but just be able to, or the reagents, just be able to know, if I tell you Kilani-Fischer synthesis, be able to tell the structures, okay, or show the product. And now we're finally getting to the last portion, and it's going to be quick. All I need you to be able to do is successfully draw glycosides. And I will give you this right now. So you have now disaccharides and oligosaccharides. So disaccharides are 2. Oligosaccharides are 2 to the 10, as I said to you. So the book states more than 6, etc. The disaccharides contain 2 monosaccharides joined together by a glycosidic linkage or a bond. Okay. So, I mean, you know, the word di means, the prefix di means 2. It means you have 2 saccharides, 2 of these groups or units. Here it is. Here is the glycosidic linkage. Here's 1 sugar, here's another, or 1 sugar, there's another. And here it is. Okay, this bond may be alpha or beta, yes, because it really depends on whether this saccharide had an alpha or a beta anomeric carbon or OH. So again, we don't know, it depends on that. And both monosaccharides rings may be 5 or 6 membered. So this could be 5, that one could be 6. The rings are connected by an O atom that is part of an acetal called the glycosidic linkage, which may be oriented alpha or beta. So the glycoside is formed from the anomeric carbon of 1 monosaccharides and any OH on the other. Okay. So let me give you examples here, then you're going to be able to draw it. So you have maltose grains, this is in grains, and you have sucrose, that's in sugar cane, and then you have lactose, that's in milk. Those are most common oligosaccharides, are disaccharides. And then you have the following are found in peas and beans. So you have raffinose, like this one right here. And you have stachyose, which has 4 of them. And then you have etc. Now, one thing we need to be able to understand about this is you you need to see, okay, how the linkages, between these are again oriented. So if you notice here, this is actually an alpha linkage because it's pointing down. Okay. Also alpha, but that one is beta to it. So again, we're going to pay attention to this momentarily in a moment. This is interesting. So these oligosaccharides are indigestible since they contain galactopyranose ring residues involving an alpha and an alpha 1,6 glycosidic bonds that humans lack the enzyme to hydrolyze. Okay, here's the one. Here's the one, because that's on the first ring, and here's 6 on the other ring. And it's alpha because it's pointing down. So it's alpha 1,6 because it's pointing down. Okay, 1 because this is always numbered 1. So, you have 1, 2, 3 as we did 4, 5, and that's 6. Same thing here, 1, 2, 3, 4, 5, and 6. So notice how this is 1 and that's 6. So that's why it's called an alpha 1 to 6 linkage. Well, if you eat beans, peas, whatever it is, and you feel bloated, maybe some may not, but you should experience some degree. And the reason why is because we don't have the enzyme to hydrolyze it, cut those bonds. And who does that? You have bacteria in your intestines, and they just feast on this, and they are able to use their enzymes to break them. And the byproduct of this is carbon dioxide. So that's why you get gassy. And you have polysaccharides. They contain larger than 10 monosaccharides joined together. The 3 most prevalent polysaccharides are cellulose, which is in wood, in plants, in paper, grass, starch, and glycogen, each of which consists of repeating glucose units joined by different glycosidic bonds. So for example, this is cellulose right here. And notice how it's 1 to 4 beta glycosidic bonds. 1 to 4 beta. It's written 2 ways. It's either 1 to 4 beta or sometimes like this, beta 1 to 4. Be able to understand, that they both mean the same thing. The reason why you can't digest cellulose, which is in grass or in woods, like if someone hungry, why can't they eat grass? Well, the reason why we can't is because you have a beta glycosidic bond or linkage, and we don't have the enzyme to cut that. We do not have the enzyme to cut that or hydrolyze it. But starch, on the other hand, is alpha. So look at the difference between cellulose, which is in grass, in paper, and starch. We know where that is. In potatoes, rice, whatever it is, bread, all of that stuff. The reason why we can hydrolyze it is we have an enzyme that actually cleaves or cuts the alpha glycosidic linkage. And notice that by M means how many of those monomers. M means monomers, and monomers means a unit. You can think of it, a unit. So here, look how many you have, between 2,000 to 26,000 units, monomer units, or the monomers, versus starch, which has actually less than 1,000. So this is much more complex cellulose than starch. Starch is the main polycarbohydrate found in seeds and roots of plants. Starch is a polymer composed of repeating unit joined by alpha glycosidic bond. Make sure You remember this, it's alpha. That's why we can digest it. And here they are. They're shown this way. So you have amylose. This is a linear form of starch. All alpha linkages from 1 to 4. 1 to 4. 1, 2, 3. Here's 4. 1, 2, 3. Here's 4. So between 1 and 4, see that? And you have amylopectin. This is a branched one. It's 1 to 6 alpha glycosidic bonds. So you actually have one of them that is 1. Here it is. It has a 1 to 6. 1 and 6 on the other one. Those are the two different forms of starch. Glycogen is the major form in which polysaccharides are stored in animals. It's a polymer of glucose containing alpha glycosidic bonds. So like ribose, and DNA, deoxyribose. Not much. I mean, this is really more so in biochem, but the reaction diribose with certain amine hydroxylic forms and glycosidic called ribonucleosides, the same reaction of two deoxyribose forms, deoxyribonucleosides. So if you notice here, here's the ribose, here's D-ribose right here. This is the D-ribose. Okay, for some reason the pen is not working very well. So let me see, let me try again. There we go. This is your D-ribose. So you have a ribonucleotide. That's only when you have one, by the way. And then this is a deoxy. Deoxy means removed one of the hydroxy groups, if you remember that from biology. That's what 2-deoxy. Deoxy means the oxygen or the hydroxy removed. Hydroxy removed. So what kind of ring is that? It's a furanose ring. It has what? It has 5, right? Okay. Ribonucleotides are the building blocks of the polymers. So again, notice that there's some kind of a reaction that occurs here. You have amines right here. All of this is biochem. What? Based on what? Organic chem. Building blocks of polymer ribonucleotide, nucleic acid, RNA, the messenger molecule that converts genetic information into proteins. Deoxyribonucleotides are the building blocks of the polymer deoxyribonucleic acid, that's DNA, the molecule that are responsible for the storage of all genetic information. So isn't it amazing that sugar really is the genetic code, again, depends. The base of it is a ring. So now what we want to do is be able to draw a polysaccharides, or let's say an oligosaccharides, disaccharides. We can do 2 of them. And I'm going to tell you how to, like, what linkages need to be in there. So let's draw that. Maybe down here if you have enough space.